So in this video, we are going to solve some various distance and displacement problems. So we need to remember what some of the symbols are that we're going to be using in these problems when we use these equations. So remember that x we're going to use for position, and you use subscripts to talk about which position you mean. So x naught, this 0 here is pronounced naught, x naught is the initial position. Sometimes I may also write xi for that, for I for initial. Sometimes I'll use it, sometimes I'll do this. xf means the final position. And this triangle symbol is delta. It's the Greek letter delta, and it always means change in. So if we're finding the displacement is the change in position, so that's what we're writing here, okay? And I'm also going to use some subscripts like the change in position 1 and change in position 2 when I have more than one change in position, more than one displacement. And I may say x1 for my first position and x2 for my second position. So any of these symbols we could be using right now. The equations that we've learned so far for displacement, we know that displacement, or the change in position, is equal to the final position minus the initial position at time 0. This is one way to find displacement. Another way to find displacement is if you have multiple displacements, you don't necessarily know what the initial position and what the final position are, but you know that they went this far, and then they turned around and went that far, and then they went this far. So you actually know how far they went as opposed to what position they were at. You could also add up displacements. So the total displacement could be found by taking your first displacement, whatever it was, they went this far, and adding that to their second displacement if they had two. And if they had more of them, then you could add however many displacements you're given in the problem. And if you add them all up, that's going to give you your total displacement for the problem. Okay, so there's two different ways to find displacement, and it depends on what information you're given. So you always have to analyze the problem. This is similar to what you're going to do for distance, because if you're looking for distance, then you would just take your first distance and your second distance and add them together. Okay, so let's look at some problems. This is the first problem that I gave you, and it's actually very simple. And most of you wouldn't even think about this as being some kind of a physics problem. It's very simple. A cyclist rides 3 kilometers west, and then they went 3 kilometers west is to the left, and then they turn around and they ride 2 kilometers east. Okay, this is where they started. We don't know what their initial position is, but we just know they started here. Okay, went 3 kilometers, turned around, and came back 2 kilometers. So we want to know their displacement, and we want to know their distance. And then we also want to find the magnitude of the displacement. And I told you about magnitude already, but we'll talk about this in a minute. To find the displacement, we had those two equations. So right here they are. And we have to look at what we're given in the problem. So what we have here, we know that the initial position was 0, okay, because they didn't give us the initial position, so we can just say she started at 0. We can call that 0. But we actually don't know what her final position is. So to be able to use this equation to find displacement, we would need to know the final position, or else we can't subtract. So we can't actually use this equation right now. We can use this equation, and that got left out. So what we have is her first displacement, because we know that she went 3 kilometers west, And then we have this second leg of the trip here, 2 kilometers east. So we can actually add those together. So this is solving for A. The first chunk of the displacement was 3 kilometers to the west, and the second displacement was 2 kilometers east. Now, we use negatives and positives to mean east and west. You can do this however you want. The fact is, she started off going west, so I would just call this west the positive direction. So when I solve this problem, if I want to find her total displacement, I'm going to use this equation here. So her first displacement is 3 kilometers. And I'm going to add that to her second displacement. But what you have to realize is that since they're in opposite directions, if we call this one positive, then this has to be negative. So we're going to add that to negative 2 kilometers, which means we're going to subtract them. And so her overall displacement is positive 1 kilometer, and since we called the positive direction west, she ends up 1 kilometer west of where she started. Now, many of you may have just been able to look at this and say, okay, well, if she went 3 this way and 2 this way, that's 1 kilometer, and she's left of where she started, so that's 1 kilometer west. And that's fine. This is a very simple problem. I worked it out because you may have ones that are harder than this, and you have to think about a little bit more, like the next problem we're going to do. But if you can do this in your head, that's fine. Okay, this is a simple problem. So what distance does she ride? Okay, so for distance, again, this is a pretty simple problem. Remember, with distance, if we have multiple distances, we're just going to add them up. And we don't care about right and left, so there are no negative numbers for distance. Everything is positive. You just add them together. So her distance, she went 3 kilometers, and then she went 2 more kilometers. So she went 5 kilometers. Pretty simple. The last question says the magnitude of her displacement. You're going to see this word magnitude frequently. Whenever you see magnitude, it means the amount. It just means answer the question. So this says, what is the magnitude of her displacement? What you should read is, what is her displacement without the sign? That's what this means. So we already found her displacement. It was 1 kilometer west. For magnitude, we don't care about the west part, 1 kilometer. So the magnitude of her displacement, you would just find her displacement and not care about the direction. That's it. Okay, we'll solve this second problem now, which is going to be similar to the one that we just solved, but it's got 3 displacements instead of 2. So if you don't need to see this part of the video and you think you can just solve this really quick, do that and then just skip ahead to where I have it answered and check your work. Okay, so Tiana is going to jog along a straight path. We don't know which direction she's going, but we're just going to say, so if we continue reading, she's then going to turn around and go 2.4 in the opposite direction and then go back in the original direction. Let Tiana's original direction be positive. So this is saying that we don't know if she's going right or left, east or west, but whatever direction she's going here is our positive direction. So she's going 1.5 kilometers this way. She turns around and goes 2.4, which is longer than 1.5. So she's going to pass her original position. And that was 2.4. And then she's going to come back 0.7. Okay, so if we want to find her displacement, again, just like in the previous problem, we don't know her final position, and so we can't do this the easy way. We have to add up her displacements. And so we know that the original direction is positive, so this is a positive displacement, this is a negative displacement, and this is a positive displacement. And so we are going to add her displacements up using this equation. There are 3 of them. So we have her first one, which is 1.5. Her second, now you're adding them up, but if you add a negative, that's subtracting. So I'm going to subtract the 2.4 and then add the 0.7. And if you put that in your calculator, you get negative 0.2. And these were all kilometers. I didn't write them here, but your answer should always have a unit on it. So what was her displacement? Her displacement was negative 0.2 kilometers. Since this was the positive direction, she actually didn't quite make it back to her starting point. She gave up jogging before she got back to where she started. That's what this is saying, right? She ended up this far from her starting point. For distance, again, we don't care about the fact that this was in the opposite direction. She probably doesn't care either. If she went jogging, she just wants to add it all up. And so if we add all of those up, I believe we get 4.9. I'm going to check that in my calculator. We get 4.6. So again, this was a little bit trickier than the last one because you had 3 displacements. And when you start figuring out what displacement is, it's pretty simple to just pick up your calculator and just do add, subtract, add. If they're going one way, you add them. If they're going the other way, you subtract them. So this problem is going to be a little bit different than the last one. Again, if you think you can do this on your own, then go ahead and do it. And then just speed up the video until I have the answer and check to make sure you're right. Okay, a car enters the interstate at mile 47, at the 47-mile marker. So if you know about driving, you know that there are those green signs and they're the mile markers. They're little. At each mile it marks how far you are from the state line. And the exit numbers equal those as well. So she would have come in at exit 47. But regardless, she starts out at the 47-mile marker, MI for mile, M for meter, MI for mile. The car leaves the interstate at 15, at the 15-mile marker. Okay. What's her distance and displacement? So with this problem, it's not saying that she went 47 miles. This is like a number line laid out. She started out at the 47-mile marker and she ended up at the 15-mile marker. So it's like a number line. She went from 47 to 15. So this is where she started. So this is her initial position. She left the interstate at her final position, which was 15. So now we have initial and final position. So we're going to use a different way to solve for displacement with this. So for her distance, again, we have to think of distance a different way as well for this one, because before we were just adding up the distances. But again, she didn't go 15 miles and then 47 miles. We can't add these together. She started out at 47 and went 15. So instead of adding these up, we actually have to subtract them because we're trying to see how far she went between these two. So 47 minus 15 is going to give us 32 miles. For displacement, we're going to use this equation because we have the initial and final positions. So our initial position is 47 miles. Our final position is 15 miles. And to find displacement, because it has direction and that direction has meaning, we're always going to do the final position minus the initial position. The final position was 15 miles. Her initial position was 47 miles. She was at the 47-mile marker. And so her displacement is 15 minus 47. And you can see you're going to get a negative number for that. So it's going to end up being negative 32. Since she was starting out at a bigger number and went to a little number, essentially she was going in the negative direction. So her displacement was negative 32 miles. That negative just means she was going in the negative direction. She was going down in numbers. notice that this is straight line motion. She wasn't going back and forth. And so the distance and displacement have the same magnitude. They're both 32. But this displacement also has direction, so negative 32. Whereas the distance didn't. It was scalar. It just was 32. So the final problem I'm going to work for you, let's go ahead and read it. Students lay out a long measuring tape on the floor and take measurements of themselves walking back and forth along the tape to different positions. One student stands at the 15-meter mark, and her group records this as her initial position. She moves to the 53-meter mark, and they record this as her second position. Positions 3, 4, and 5 are recorded as 89 meters, 12 meters, and 22 meters respectively. What is the student's distance, displacement, and the magnitude of her displacement? What we have here, it's not saying that she moved 15 meters and then she moved another 53 meters. It's saying she started out on this number line tape measure at 15 meters and then moved to the 53-meter mark. So again, it's like a tape measure, and if this is 0, then she started out at the 15-meter mark, then she moved, so this is her initial position, and then she moved to the 53-meter mark, which is somewhere over here. That was her second position. And then her third position was at 89 meters, way down here. And then she moved back to 12 meters, past where she started. This was her fourth position. And then she moved to 22 meters, that's over here. And that's her fifth position, or her final position. Okay. So she went back and forth, right? Here, here, way back here, and then back there. Because we have different positions, we kind of have to think about this. So for displacement, that's actually the easiest thing that we can do for this one. So we'll find her displacement first. So we don't have individual displacements. We have the positions. And so for displacement, it really doesn't matter that she went back and forth, front and back. All we care about is her initial position and her final position. So her initial position, so we need to do final minus initial position. Her initial position, sorry, I like to write I also. Her initial position is right here at 15. And her final position was at 22. So her displacement was 7 meters. And she went this way, right? So it's 7 meters to the right, from 15 to 22. That's her displacement. Done. If you have initial and final position, displacement's super simple. Distance is actually going to be a little bit trickier on this one. So she started out at 15, and she went to 53, and then the next one she went to 89. And so this first distance that she went was from 15 to 89. We can, since she's still going in the same direction, we don't even have to worry about that, right? So we could find this one and then this one, but I'm just going to find the big one overall. So 89 minus 15 in my calculator. So to get from 15 to 89, she went 74 meters. Then she went from 89 to 12. She went back this whole chunk there. So distance 2, she went from 89 to 12. And we don't care which direction, so we don't need to get a negative number. And so 89 to 12, 89 minus 12 is 77. And then from 12 meters, then she moved to her final position of 22 meters. And so that third chunk there, she went, is the distance between 12 and 22, so I'm going to subtract those, and that's 10 meters. And so then for the total distance, I'm going to add these together. Total distance, I'm going to add D1 plus D2 plus D3. And that means I'm going to add 74 plus 77 plus 10. She went a total of 161 meters. So that one was actually a little bit trickier because you had to think a little bit harder to figure out how far she went. Okay, one last thing that I want to say before moving on is that often you're going to get, especially right now in this unit when we're dealing with distances, you're going to get all sorts of different units. The SI unit, the Standard International Unit for distance, is a meter. And once we get past this unit, we'll usually just use meters for distance. But right now, to mix it up a little bit, you know, we're going to talk about miles, you'll get kilometers, you'll get meters, and you saw all those in the problems that we had. And you have to be able to convert between them. So one thing to remember is that if you have multiple units for distance, if you are adding up, say, 2 kilometers plus 3 miles plus 4 centimeters, you can't just add these that easily. They all have to be in the same unit. So you would need to either convert them all to kilometers or convert them all to meters. However you need to do this. So I didn't give you any of these today, but just be aware that you do need to have all the units matching before you can add them, because this would not be 2 plus 3 plus 4, because 4 centimeters is just a teeny little bit of a kilometer, right? This would be 4 centimeters is 0.000004 kilometers. So to add these two together, you would have to do, it would be 2.000004 kilometers. And then to add in the 3 miles, you would have to change that to kilometers as well. So there's about 1.6 kilometers in a mile, so you'd have to do 1.6 times 3, which is, if my math serves me, 4.8. And so then you could add 2 plus 4.8 plus that, and that gives you 6.800004 kilometers. Okay, I'm not asking you to do this right now, but I just want you to be aware that you have to pay attention to units. Okay, so I've given you these practice problems. You can go ahead and pause the video now if you need more practice and work these, and then you can play the video, or you can just, skip to where the answer is just to check your answer.